As Okay, Assalamualaikum warahmatullahi wabarakatuh. So this is the week 2 notes. Okay, notes for week 2, which is series resistor, voltage division, and resistor and current divisions. Okay, so what is a series resistor? So series resistor is the, for example, we have two resistors as in this, as shown in this circuit, are considered in series if the same current pass through them. So this is that is we call the resistor are in series, and applying the Ohm's law to the both resistors. So V1 is equal to I R1, and the voltage drop V2 is equal to I R2, and apply the KVL inside this closed loop. So we obtain negative V1 plus negative V plus V1 plus V2 is equal to 0, and then we rewrite again equation. So V is equal to the total of the voltage drop, where the total of the voltage drop it's actually I multiply with the summation of all resistors. So meaning that therefore, okay, what we can conclude here is that for a resistor that connected in series, they can be equivalent to a single resistor, where the value of the R equivalent is actually the summation of two resistors. Okay, so meaning that if you have a resistors, a number of resistor that is connected in series, so you can just simplify the circuit, okay, to be represented by a single resistor R equivalent, where this value of R equivalent is actually the summation of all resistors that are connected in series. And this is about the parallel resistor. So when two resistors are in parallel, the voltage drop across them are the same. For example, this circuit, okay, the voltage drop across R1 is V1 is V. The same goes to the voltage drop across R2 is also V. So V is equal to I1 R1, which is equals to I2 and R2, or we can write down this as a I1. Okay, I1 is the current branch that going flow to resistor 1, and I2 is the branch current that through the resistor 2. So I2 is equal to the voltage across the resistor over the R2. And based on the KCL, where we not, okay, this is not A, okay, so the total current is I. So based on this KCL, so I is equals to the summation of all the branch current. Okay, that, okay, so therefore what we can conclude that for a resistor that are parallel, okay, you can actually represent this R1 and R2 as a R equivalent, which is R equivalent is equals to this one, R1 multiplied with R2 over R1 plus R2. So how we get this is actually based on this derivation. Okay, so for a resistor that equivalent and connected in series, for example, you have a resistor with a value of 10, and then you have a number of, for example, you have 3 resistor connected in parallel. So the R equivalent is actually R over the number of parallel branch. So if R so is 10, so this is R10 over 3. So your R equivalent is actually 3.33 ohm. Okay, so this is applied only when you have a resistor that have a same values that connected in parallel. Okay, you just divide it with the number of the branch that are parallel. Other than that, you need to use these equations. Okay, so my question is, what happened when you have like this? You have this one is 5 ohm, and you have this one is 10 ohm, and another one is actually 2 ohm. So how can you get the R equivalent that see from this terminal? So these three branch are parallel. 5 ohm is parallel with 10 ohm and parallel with 2 ohm. Okay, so how to do this? Okay, so what we need to do is to simplify first the circuit with we need to actually parallel first R and 10 parallel, and then after we have finished parallel this R and 10, then after that then we can parallel up with 2 ohm. So R parallel with 10, so you have R 10 5 multiplied with 10 over 5 plus 10, so this one will become 50 over 15. Okay, so 50 over 15 by using calculator. Okay, sorry, 50 over 15 is 3.33. Okay, oops, sorry. So this one 3.33, and then so you need, after that, so you need to parallel up with the ohm, with 2 ohm. So the R equivalent is 3.3 parallel with 2, or 3.3 multiplied with 2 over 3.3 plus 2. Okay, so that is how we do. If you have a 3, for example, this one 10, so this one is 5, this one is 2. So how? So this is how we do it. You need to parallel up this first, and then after you have equivalent parallel equation, parallel value, which is 3.3, then you proceed with parallel up with this one. So 3.3 parallel with 2. So it has 2 steps. Okay. And if you have a resistor that are equivalent in values, so you just have that value or divided by the number of branch that is parallel. Okay, this one I think I skipped. Okay, so example, find the equivalent resistor value for this circuit. Okay, so this is R equivalent sees from this terminal. So what is the R equivalent values that can be seen from this point? So what is your R equivalent? So what you need to do is to identify which branch are parallel and which branch are series. For example, this one is actually in series, so this one becomes 6 ohm. Okay, and this one is actually parallel, so 6 parallel with 3, so this one 3 multiplied with 6 over 6 plus 3, so this one is 18 over 9, so this one become 2 ohms. Okay, so 2 ohms and 2 ohms. So right now we have simplified the circuit like this for, okay, and then we have to, so we have simplified the circuit like this. So this one 2 ohm, this is one also 2 ohm, so this one is actually 6 ohm, and this one is 8 ohm. Okay, so right now, so this one parallel. Okay, so 6 parallel with 4, you have 6 multiplied with 4 over 6 plus 4, so 24 over 10, so this one is 2.4 ohm. Okay, so meaning that you have 4, 2.4, and then 8. So your R equivalent is, so right now the all 3 resistors are in series, so you just sum up, so 4 plus 2.4 plus 8, so this one is become 14.4 ohm. So that is your R equivalent, that values that see from this terminal. Okay, this one example 2.29. I leave it for you to do the exercise. So this is exercise for you. So please do it, and then we will. I will ask what is the answer for this example. Okay, and this one. Okay, let's try this one. So we have. It's quite weird. Okay, it looks like weird. So we have this terminal. Okay, we also have this terminal. So but the question is actually what is the R equivalent that sees from this point, this terminal. Okay, so this is open circuit, meaning that the current will not go here. So we can ignore this one, this branch, because the current, if you put a voltage source here, the current will not flow through this branch because this is open circuit. Okay, this one also, the current will not go here. So meaning that the functional circuit, if you put voltage source, you will have a current flow through these elements only. So meaning that your R equivalent, so right now all are actually in series. So just sum up. So 25 plus 180 plus 60 ohm, which is the answer is 265 ohm. Okay, voltage division. So here we will derive what we call the voltage division formula. For example, we have a shortcut, okay, to obtain the value of V1 or V2 by having a very short, what we call a very fast method. Okay, so how to derive the formula? So we assume that this is the circuit like this. So based on the KVL, the voltage source is equal to all the summation of the voltage drop. And we know that these resistors are in series. Okay, so the current is actually the same current. So we can factor out the current here. So R1 plus R2, where R1 and R2 is actually your R equivalent. Okay, and we know that from here we can find that your I is equals to V over R equivalent. Okay, and we know that V1 is IR1. So by inserting back V here to this, okay, so you will have VR equivalent multiply with R1. So what is your R equivalent? Is V R1 plus R2 multiply with R1. The same case goes to V2. V2 is I R2, where your I is V R1 plus R2 multiply with R2. So this is the formula. Okay, this is the formula used to calculate the voltage drop much more easier. So this is what we call the voltage division formula. Okay. So V1 is actually R1 over R1 R2 multiplied with the voltage source, while for V2 is R2, the resistor itself over your total resistor multiply with your V source. Okay. And this is the current division. So when you have two resistors that connected in parallel, okay, so you can actually get the current equations equal to this formula. So you can directly calculate I1, the current branch I1 and I2 by using this formula. So for example, to get the I1, what you need to do is the R2 over the total resistance multiply with the total current from the source. While to get the branch current I2, what you need to do is actually take the R1, okay, over the total resistor and multiply with the current. Okay, I think that's all for today. So we will proceed with next class. Thank you very much.